We see a reflection of a sunset, then the face, then the person standing on a cliffside. The camera continues to pull back until the Earth is just a marble, then a speck, then a pale blue dot suspended in a sunbeam. Everything you've ever known, every war fought, every love story whispered, every empire that rose and fell, exists on this tiny, fragile grain of sand. For centuries, we viewed our world as the center of all things. Then we looked up. We found the sun, a roaring furnace so vast it could hold 1,000,000 Earths inside its belly. To us, the sun is the ultimate definition of power. It is the anchor of our reality, a stable, perfect sphere that follows the laws of physics with absolute precision. But as we leave the warmth of the inner solar system, passing the frozen rings of Saturn and the lonely dark plains of Neptune, we are about to encounter something that shouldn't exist. We are racing 19,000 light-years away, deep into the dust-choked corridors of the Scutum Centaurus arm of the Milky Way. Out here, the rules of the universe begin to fray at the edges. Out here, we find the king of stars. Visual. The camera speeds up, stars becoming streaks of white light. We dive into a thick, glowing red fog of interstellar dust. Suddenly the fog clears, and a wall of ruby-red light fills the entire screen. This is Stephenson 2-18. At first glance, it looks like a star, but look closer. Most YouTube videos will tell you it's simply the biggest. They'll show you a size comparison and move on, but they're missing the most terrifying part of the story. Stephenson 2-18 isn't just an outlier, it is a physical impossibility. To understand why, we have to look at the benchmark. For decades, the giants of our sky were stars like Betelgeuse or Antares. They are monsters in their own right, but they follow a specific cosmic code. According to the cosmic limit theory, there is a ceiling for how large a star can grow. Astrophysics tells us that once a star reaches approximately 1,500 solar radii, the balance between gravity pulling in and radiation pressure pushing out becomes so precarious that the star should literally tear itself apart. 1,500 is the hard limit. It is the point where a star ceases to be a solid object and becomes a chaotic, unstable mess. And then we measured Stephenson 2-18. The result? 2,150 solar radii. Visual. A graphic showing the 1,500 limit line. A silhouette of a normal red supergiant sits right at the line. Then, the silhouette of Stephenson 2-18 appears, towering nearly 50% higher than the impossible limit. This isn't just a new record. It's a crisis in physics. If our measurements are correct, Stephenson 2-18 is standing in a region of space where no star has the right to exist. It has crossed the limit of impossibility, shattering our models of stellar evolution. If you replaced our sun with this monster, the scale wouldn't just be big, it would be an apocalyptic reorganization of space-time. Mercury wouldn't just be engulfed, it would be gone before the star even touched it. Venus, Earth, Mars, all swallowed. But it doesn't stop there. The surface of Stephenson 2-18 wouldn't just reach Jupiter, it would extend all the way to the orbit of Saturn. Imagine standing on the moon of Uranus, looking back toward the center of the solar system. Instead of a distant bright dot of a sun, you would see a wall of red fire spanning the entire horizon, a sunset that never ends, because the star is so vast it dominates the very fabric of the sky. But there is a reason this star looks different. Visual. High-resolution close-up of the star's surface. Instead of a smooth sphere like our sun, it looks turbulent, boiling, and lumpy. If you could fly a ship to the edge of Stephenson 2-18, you wouldn't find a clean, defined surface. You would find what astronomers call a lumpy reality. Because the star is so physically bloated, the gravity at its outermost edge is incredibly weak. It is so weak that the surface is essentially a luminous vacuum. The star is breathing. Enormous, boiling convection cells, some the size of entire solar systems, churn and bubble, throwing pillars of plasma millions of miles into the void. It's not a sphere. It's a terrifying, glowing web of gas that is barely holding onto itself. It is a star that is essentially a hollowed-out ghost, containing the volume of 10 billion suns, yet weighing only about 40 times as much. Think about that paradox. It has the volume of a god, but the density of a cloud. This brings us to the ultimate mystery, the one the other documentaries won't tell you. How is it still here? By all the laws of thermodynamics, the radiation pressure from its core, a core fusing helium and heavier elements at a rate that defies logic, should have already blown these outer layers into the interstellar medium. The star should have shed its skin and collapsed into a black hole eons ago. And yet it remains, glowing with a luminosity of 440,000 suns, sitting in the darkness of the Stephenson 2 cluster like a giant that refuses to die. Is it possible that our math is wrong? Are we looking at a star that has found a glitch in the laws of gravity? Or is there something even more unsettling happening, a measurement illusion that has tricked every telescope on Earth? Visual. The camera pans across the distorted, lumpy surface of the star as the music turns from awe-inspiring to eerie and mysterious. We aren't just looking at the largest star ever discovered. We are looking at a benchmark of human ignorance. Stephenson 2-18 is a reminder that the universe doesn't care about our limits. It doesn't care about our theories or our hard boundaries. In this documentary, we aren't just going to show you how big it is. We are going to investigate the lore of the impossible. We're going to dive into the infrared fog to find out if this star is a real physical object or a cosmic mirage that is forcing us to rewrite the history of the stars. The King of Stars is waiting, and it's far more mysterious than you've been led to believe. Visual. A split screen. On the left, a traditional telescope view of the night sky, dark, empty patches of the Milky Way. On the right, the same patch of sky viewed through an infrared filter, suddenly exploding with thousands of hidden red points of light. For thousands of years, humanity looked at the constellation Scutum and saw a graveyard. To the naked eye, and even to the most powerful optical telescopes of the 20th century, this region of the Milky Way appeared as a zone of avoidance, a vast, impenetrable wall of soot and cosmic smoke. We knew the galaxy was dense, but here, in the Scutum Centaurus arm, the universe seemed to have drawn a curtain. It is one of the great ironies of astronomy. The largest star ever discovered was hidden in plain sight, masked by particles of dust no larger than the smoke from a cigarette. To understand how we found Stephenson 2-18, you first have to understand the infrared fog. Space is not a vacuum of perfect clarity. It is a dark forest filled with interstellar dust. This dust is a master of deception. It excels at a process called extinction, absorbing and scattering visible light until a star as bright as 1,000,000 suns is reduced to a flicker that can't even reach our eyes. But in 1990, an astronomer named Charles Bruce Stephenson did something that changed our map of the cosmos forever. He stopped looking at the light we can see and started looking at the heat we can feel. Visual, a cinematic 3D map of the Milky Way. We see the spiral arms. A heat-seeking beam sweeps across the Scutum Centaurus arm, revealing a massive, glowing cluster of red dots. Using deep infrared surveys, Stephenson pierced the veil. What he found wasn't just a star, but an entire city of giants, the Stephenson 2 cluster. This is one of the most massive assemblies of red supergiants ever found in the universe. Imagine a neighborhood where every resident is a monster, each one hundreds of times larger than our sun. But even in this city of titans, one inhabitant stood out. One star was so bright, so overwhelming in its infrared signature, that it initially looked like a mistake in the data. This was Stephenson 2-18. The discovery was a technological triumph, but it immediately gave birth to a mystery that still haunts astrophysicists today: the distance paradox. You see, calculating the size of a star is a delicate game of cosmic geometry. To know how big it is, you must know exactly how far away it is. Most of the outlier videos you've seen treat the distance of 19,000 light-years as a proven fact. But the lore vault tells a different story. Visual, a graphic demonstrating parallax. We see the Earth orbiting the Sun and the tiny shift in a star's position. The graphic shows the line of sight becoming shaky and uncertain as it stretches deep into the scutum arm. For nearby stars, we use parallax, a form of celestial triangulation. It's the most accurate tool we have. But parallax only works out to about 400 light-years. Beyond that, the angles become too tiny, too blurred by the very dust that hid the star in the first place. For Stephenson 2-18, located nearly 19,000 light-years away, we are essentially guessing in the dark. We estimate its distance based on its membership in the Stephenson 2 cluster. But here is the glitch that mainstream documentaries ignore. Stephenson 2-18 doesn't sit at the heart of the cluster. It sits on the outskirts. In the world of stellar evolution, this is a red flag. If Stephenson 2-18 is actually a few thousand light-years closer to Earth than the rest of its cluster, its impossible size of 2,150 solar radii would vanish. It would shrink from a record breaker to a normal supergiant. We would be victims of a measurement illusion, a perspective trick played by the geometry of the Milky Way. However, the infrared data suggests something far more chilling. Visual, a spectral analysis chart. Lines of titanium oxide and vanadium oxide appear like a barcode. The lines are thick and distorted. When we analyze the light of Stephenson 2-18 using spectroscopy, we see the fingerprints of an ultra-cool, ultra-extended atmosphere. We see heavy molecules like titanium oxide, substances that can only exist in the outer layers of a star that has ballooned to a truly grotesque scale. The spectral data confirms that this isn't just a regular star that looks big because it's close. It is a star whose physical structure is fundamentally wrong. This brings us to the heart of the hiding mystery. Why was the king found at the edge of the cluster and not in the center where the gas is densest? There is a fringe theory, often whispered in the lore vault, that Stephenson 2-18 wasn't born a giant. It's possible that it is a competitive accretor. In the crowded, chaotic nursery of the Scutum Centaurus arm, this star may have been a cosmic bully. While its neighbors were forming into standard stars, Stephenson 2-18 may have been positioned in a sweet spot of gas flow, gorging itself on the surrounding molecular cloud, stealing the mass that should have gone to thousands of other stars. It grew so fast and so large that it began to drift away from the gravitational center of its cluster, a bloated king leaving its kingdom behind. Visual, the camera moves through a dark forest of gas and dust. We see the ruby-red glow of Stephenson 2-18 in the distance, illuminating the surrounding fog like a lighthouse in a storm. But even as infrared telescopes like Spitzer and Gaia give us clearer views, the fog remains our greatest enemy. The dust doesn't just hide the star, it changes its color. This is called reddening. The dust filters out the blue light, making the star appear even redder and cooler than it actually is. This uncertainty creates a margin of error that could hide a star's true nature for decades. Is it a record-breaking titan that defies the 1,500 limit? Or is it a clever illusion, a star wearing a dusty mask that makes it look larger than the laws of physics allow? As we peer through the infrared veil, we aren't just seeing a star. We are seeing a challenge to our perception. We are realizing that the king of stars might be the ultimate test of human measurement. If we are wrong about the fog, we are wrong about everything. But if we are right, then we have to face the most terrifying possibility of all, that the universe is capable of building something that our math simply cannot explain. Visual, the infrared glow of the star begins to pulse, like a slow, deep heartbeat. The ruby light washes over the screen. The curtain has been pulled back. The ghost has been found. But as we step closer to the luminous vacuum of its surface, we are finding that the truth is far more unstable than the dust that once hid it. We see a red supergiant star pulsing. A red caution line appears at the 1,500 mark. The star swells past it, and the hologram begins to flicker and spark with error messages. In every branch of science, there are lines you simply do not cross. In physics, it's the speed of light. In thermodynamics, it's absolute zero. And for decades in the study of the heavens, there was a cosmic ceiling for the size of a star, 1,500 solar radii. This wasn't just an arbitrary number. It was a mathematical wall built by the very forces that allow stars to exist. But today, that wall has a 2,150 solar radii-sized hole in it. To understand why Stephenson 2-18 is causing a crisis in modern astrophysics, we have to look at the delicate tug of war that keeps a star from either collapsing into a black hole or exploding into a cloud of gas. Scientists call this hydrostatic equilibrium. Visual: a cross-section of a star. Blue arrows point inward, gravity, and orange arrows point outward, radiation pressure. They meet at a stable, glowing surface. Inside the core, a star is a continuous, controlled nuclear explosion. It fuses hydrogen into helium, and later, helium into heavier elements like carbon and oxygen. This process generates an incredible amount of outward pressure. Gravity, meanwhile, is trying to crush all that mass back down into the center. For most of a star's life, these two forces are perfectly matched. But as a star enters its twilight years and becomes a red supergiant, it starts to lose its grip. Visual: the star begins to balloon. As it gets larger, the blue gravity arrows become thinner and more translucent, while the orange radiation arrows grow jagged and violent. The larger a star gets, the farther its surface moves away from the gravitational anchor of its core. Think of it like holding onto a spinning merry-go-round. If you're at the center, it's easy to stay on. But as you move toward the outer edge, the force trying to throw you off becomes overwhelming. According to traditional models, 1,500 solar radii is the point of no return. At this distance, the gravity at the star's surface is so incredibly weak that the outward radiation pressure should simply win. The star's outer layers shouldn't be able to stay attached. They should be blown away into the void by the star's own light, leaving behind a smaller, hotter core. For years, every star we found fit this model. Betelgeuse, the famous giant in Orion, sits comfortably around 800. Antares is roughly the same. Even the previous record holders like VY Canis Majoris seemed to respect the 1,500 limit after more accurate measurements were taken. And then came the data for Stephenson 2-18. Visual: a scale comparison. Our Sun is a pixel. Betelgeuse is a marble. The 1,500 limit line is a wall. Stephenson 2-18 is a massive sphere that simply ignores the wall, extending far beyond it. At 2,150 solar radii, Stephenson 2-18 isn't just big, it is 43% larger than the maximum size allowed by the laws of stellar physics as we knew them. It is a star that has walked off a cliff and refused to fall. This creates what the lore vault calls the Eddington crisis. The Eddington limit is the absolute maximum luminosity a star can reach before its own light is so powerful that it overcomes its gravity. Most massive stars have a luminosity limit of around 320,000 suns. Stephenson 2-18 has been measured at 440,000 suns. It is radiating energy with such violence that, by all rights, it should have shredded itself into a nebula long ago. Yet, when we look at it through our infrared eyes, it appears relatively stable. It's not currently undergoing a cataclysmic eruption. It's just sitting there. Visual: close-up of the star's surface. We see convective cells the size of our entire solar system. They look like boiling bubbles of plasma, shifting and churning. This leads to a terrifying question for astronomers. Is our understanding of gravity wrong, or is our understanding of light wrong? One theory suggests that we are witnessing a new kind of luminous hydrodynamics. It's possible that at this extreme scale, the star's atmosphere isn't a solid surface, but a luminous web, a tenuously bound cloud of plasma that is constantly being shed and recaptured in a cycle we've never seen before. But there's another, more unsettling possibility hidden in the spectral data. Some researchers believe Stephenson 2-18 is cheating the 1,500 limit because it isn't a single star at all. Visual. The star's core is highlighted. Instead of one point of light, we see two cores spiraling around each other inside the same massive envelope. This is the monster merger theory. In the crowded environment of the Stephenson 2 cluster, it's possible that two massive stars collided and merged. This would explain the impossible size and luminosity. It's not one star breaking the rules, but two stars caught in a violent, bloated union, masking their true nature behind a single, massive photosphere. Whether it's a merger or a single star-defying physics, the existence of Stephenson 2-18 has forced astrophysicists back to the drawing board. It serves as a natural laboratory, pushing our computer simulations to their absolute breaking point. We are finding that when you reach the edges of the galaxy's scale, the standard textbooks become useless. We are looking at a star that is essentially boiling its way through space-time, testing the very limits of how much matter can be held together in one place. But if the star is truly this large, it leads us to a second, even more complex mystery. If it's truly 2,150 solar radii, then its calculated distance must be exactly 19,000 light-years. If we are wrong about the distance by even a fraction, the king is nothing but a shadow. Visual. The camera pans away from the limit crisis and looks toward the vast, dark distance between the star and Earth. A ruler appears, but the markings are blurry and shifting. In the next chapter, we dive into the measurement illusion. We have to ask, is Stephenson 2-18 the largest star in the universe, or is it the greatest optical trick the cosmos has ever played on us? The markings on the ruler begin to blur and shift as it moves deeper into the galaxy. In the foreground, we see a hand trying to steady a telescope, but the image of a distant star keeps flickering and distorting like a mirage in the desert. In the world of astronomy, size is a secondary measurement. Before you can ask, how big is it? You must answer a much more difficult question. How far is it? This is the Achilles heel of Stephenson 2-18. Our entire understanding of this star as a king rests on a foundation of math that is surprisingly fragile. If our distance estimate is off by just a small margin, the giant doesn't just shrink, it evaporates into a footnote of astronomical history. This is the measurement illusion, a cosmic perspective trick that has fooled us before and may be fooling us again right now. To understand the stakes, we have to look at the stellar throne and the ghosts of the kings who came before. Visual, a Hall of Fame gallery of stars. A golden crown sits on a pedestal. We see the silhouette of VY Canis Majoris, which is then moved aside. Then UY Scuti, once the undisputed champion, appears. A debunked stamp slams across its image. For much of the last decade, UY Scuti was the monster under the bed for astrophysicists. We believed it had a radius of 1,700 solar radii, firmly comfortably above the impossible limit. But in 2018, the European Space Agency's Gaia spacecraft released a tidal wave of new data. Using high-precision parallax, the gold standard of distance measurement, Gaia revealed that UY Scuti was much closer to Earth than we thought. The result was a brutal demotion. UY Scuti's impossible radius was revised down to a mere 755 solar radii. It wasn't a record breaker. It was just a regular supergiant with a very good publicist. It had been an illusion, a star that looked large only because we had miscalculated its place in the cosmic grid. Now, the same shadow of doubt is creeping towards Stephenson 2-18. Visual, a geometric diagram. We see Earth on one side and Stephenson 2-18 on the other. A thin triangle connects them. The word parallax appears, but it is crossed out with the text, limit reached, 400 light-years. Here is the problem. Standard triangulation, or parallax, only works for our backyard, stars within about 400 to 1,000 light-years. Stephenson 2-18 is located approximately 19,000 light-years away. At that distance, the angle of shift we need to measure is so microscopic that it's like trying to measure the thickness of a human hair from across a football stadium. Even Gaia, our most advanced astrometry tool, struggles to provide a definitive geometric distance for objects this far back in the Scutum Centaurus arm. So, how did we get the 2,150 solar radii number? We used an indirect method, cluster association. Visual, a 3D map of the Stephenson 2 cluster. A dense ball of stars in the center. Stephenson 2-18 is highlighted, noticeably far away from the center, sitting on the lonely outskirts. We assume Stephenson 2-18 is 19,000 light-years away because it is named after the Stephenson 2 cluster. If it was born in that cluster, it must be at the same distance as the cluster. But look at the data provided in the lore vault. Stephenson 2-18 is a radical outlier. It doesn't sit in the heart of the cluster. It sits on the fringe. It is also significantly brighter than any other star in that cluster. Some astronomers are now asking the heretical question. Is Stephenson 2-18 actually a member of that cluster, or is it a foreground object? If Stephenson 2-18 is actually just 10,000 light-years away, still a massive distance but much closer than the cluster, it would shrink instantly. Its impossible radius would fall back below the 1,500 limit. The king would be revealed as another UY Scuti, a cosmic mirage. But the mystery goes even deeper than distance. Even if we knew the distance to the inch, we still have to define where the star actually ends. Visual. A high-speed 3D simulation of the star's surface. It's not a solid sphere. It looks like a boiling, translucent sea of red fog. Massive plumes of gas are being ejected into space, creating a shroud around the star. In our sun, the photosphere, the surface where light is emitted, is a relatively sharp line. But in a red supergiant like Stephenson 2-18, the gravity at the edge is so weak that the atmosphere is essentially a luminous web. The star is lumpy. It has enormous convection cells, some larger than our entire solar system, that rise and fall in a chaotic dance. This creates a measurement crisis. When we look through our telescopes, are we seeing the true surface of the star, or are we seeing a dense cocoon of dust and gas that the star has recently exhaled? Red supergiants are notorious for mass loss. They breathe out material at a staggering rate, creating circumstellar shells that can mimic the appearance of a larger diameter. If we are measuring the dust bubble instead of the star's edge, we are inflating the king's ego by hundreds of millions of miles. Visual. A split screen of two spectral charts. One is clean and sharp. The other, representing Stephenson 2-18, is a jagged, messy forest of lines. Words like titanium oxide and vanadium oxide pop up as the lines fluctuate. To solve this, we use spectroscopy. We look for the chemical fingerprints of the star's atmosphere. The lore vault reveals that the spectrum of Stephenson 2-18 shows signs of an ultra-cool, ultra-extended atmosphere. The presence of molecules like titanium oxide suggests a density so low it's hard to call it a star in the traditional sense. It's more like a stellar nebula that is still pretending to be a single object. This is the heart of the illusion. Our instruments are pushed to their absolute limits. We are using every trick in the book, from infrared interferometry to radiative transfer modeling, to pierce the veil. But the star is fighting back. It uses its own instability, its own breathing pulsations, and its own dusty shroud to hide its true dimensions. So, we are left with a cosmic stalemate. Is Stephenson 2-18 a record-breaking titan that proves our models of the universe are wrong? Or is it the ultimate optical trick? A star that has combined a miscalculated distance with a bloated, dusty atmosphere to fake its way into the history books? Visual. The camera pulls back, showing the star flickering behind a thick cloud of cosmic soot. The light turns from a bright, defiant ruby to a pale, uncertain orange. If Stephenson 2-18 is a lie, then our physics is safe. The 1,500 limit remains a hard wall, and the universe makes sense again. But if it's the truth, if that measurement of 2,150 solar radii is real, then we aren't just looking at the largest star. We are looking at a monster star that defies every law of gravity we have ever written. And that brings us to the most controversial theory of all. If it is that large, it cannot be a normal star. It must be something far more violent. It must be a monster merger. The camera is diving toward the horizon of Stephenson 2-18. As we get closer, the perfect circle of the star begins to distort. It starts looking less like a sun and more like a boiling ruby-red storm system. Enormous bright bubbles of plasma the size of entire solar systems rise and sink into the depths. If you were to fly a spacecraft toward our sun, you would eventually hit a clear, defined boundary, the photosphere. It's a sharp, blinding edge where the gas becomes dense enough to emit light. But as we approach the king of stars, our traditional maps of what a star is begin to melt away. Welcome to the lumpy reality. Most documentaries show Stephenson 2-18 as a smooth, glowing marble. They use the same stock assets they use for the sun, just scaled up. But the science tells a far more violent and chaotic story. Because this star is so physically bloated, stretching its volume across 10 billion suns, it has reached a state of structural fragility that is almost impossible to comprehend. At the edge of Stephenson 2-18, gravity is an endangered species. Visual, a graphic showing a gravity meter. As we move from the core to the surface, the needle drops into the red, extreme low zone. We see particles of gas simply drifting away from the star, barely held by its pull. Because the surface is nearly 1 billion miles away from the core, the gravitational grip is incredibly weak. Out here, the surface isn't a solid or even a dense gas. It is a luminous vacuum. The density is so low that if you could bring a piece of this star's surface back to Earth, it would be thinner than the air at the top of Mount Everest. This creates a phenomenon that modern 3D hydrodynamics are only just beginning to map. Instead of a smooth sphere, the star is a collection of lumps. These are colossal convection cells, titanic bubbles of hot plasma rising from the interior. In our sun, these bubbles are about the size of a large city. In Stephenson 2-18, a single bubble of boiling gas could comfortably swallow the entire orbit of Earth. Visual, a high-resolution simulation. We see a bubble on the star's surface. We overlay an image of the solar system. The bubble is larger than the distance from the sun to Mars. The star doesn't just sit there, it breathes. As these solar system-sized bubbles rise, they cool and darken, eventually sinking back into the depths. This creates a surface that is constantly shifting, warping, and bulging. It is a luminous web of gas that is barely holding on to its own center. This is why, when astronomers look at the light curves of this giant, they don't see a steady glow. They see a chaotic, irregular flicker. The star is pulsating, expanding, and contracting rhythmically as it struggles to balance the outward push of its 440,000 sun luminosity against the dying gasp of its gravity. But this lumpy nature leads us to a deeper, more unsettling mystery, one that calls into question if we can even call this a star anymore. Visual, the camera pans through a thick red fog surrounding the star. We see flashes of lightning-like energy in the gas and massive shocks moving through the atmosphere. Because the gravity is so weak, Stephenson 2-18 is effectively a mass loss factory. It is shedding its own skin at a rate that is nearly unprecedented. It is breathing out millions of times more material than our sun does via the solar wind. This material, rich in heavy elements like oxygen, carbon, and silicon, doesn't just disappear. It forms a gargantuan circumstellar shroud around the star. This shroud is a mix of gas and newly formed cosmic dust. It acts like a smokescreen that reddens the star's light and blurs its edges. And this is where the lore gap becomes a chasm. Are we measuring the star, or are we measuring its breath? If the star is as lumpy and diffuse as the data suggests, the very definition of its radius becomes a philosophical debate. Where does the star end and the nebula begin? Some theorists suggest that Stephenson 2-18 isn't a single object at all, but a stellar nebula, a core that has puffed out so much material that it is essentially a star living inside its own corpse. Visual, a split screen. On one side, a solid star model. On the other, the cloud star model, a small, intense core surrounded by a massive, lumpy, translucent web of fire. This structure is a physical paradox. If you were to look out from a planet orbiting within the outer layers of this star, you wouldn't see a sky. You would see a churning red fog that never ends. There would be no horizon, no day, and no night. Just a luminous vacuum of 3,000-degree plasma, forever boiling in a state of chaos. This is the price of being the king. To grow this large, you must sacrifice your stability. You must trade your solid form for a bloated, lumpy existence on the edge of total disintegration. And as this star sheds its mass, thinning its envelope until it's barely a ghost, it is setting the stage for its final act. It is revealing its mass-radius paradox, how an object that occupies the volume of 10 billion suns can be so incredibly light, and why that lightness is exactly what makes it so dangerous. Visual, the lumps on the surface begin to glow with an intense, blue-white heat from deep below. The music shifts from a low thrum to a rising orchestral tension. In the next chapter, we look at the weight of the king. We have to ask, how can a star this big be so empty? In the previous chapters, we've looked at the terrifying scale of Stephenson 2-18. We've stood on the moons of the outer solar system and watched as its ruby-red wall of fire consumed everything from the sun to Saturn. We've explored the lumpy reality of its surface, where convective cells the size of planets boil and churn. But now, we have to address the most mind-bending contradiction of all, a secret hidden within the star's very weight. This is the mass-radius paradox, and it reveals that the king of stars is not the solid, heavy titan you might imagine. In reality, Stephenson 2-18 is a hollowed-out ghost, a celestial marshmallow so diffuse it barely qualifies as a solid object. To understand the mystery, we have to look at two numbers that simply don't belong together. First, the volume. Stephenson 2-18 is so vast that you could fit 10 billion suns inside it. If our sun were a single grain of sand, Stephenson 2-18 would be a sphere nearly the size of a two-story house. Given that scale, your intuition tells you it should be the heaviest thing in the galaxy. You'd expect it to weigh billions of times more than the sun. But the data tells a different, much more unsettling story. Current estimates place the mass of Stephenson 2-18 between 30 and 50 solar masses. Think about that for a second. It has the volume of 10 billion suns, but it only has the weight of about 40. This is the definition of a cosmic paradox. If you could take a gallon-sized bucket of material from the outer layers of Stephenson 2-18 and bring it to Earth, it wouldn't just be lighter than air, it would be a luminous vacuum. The density of this star is so incredibly low that it challenges our very definition of what a star is. It is a giant, glowing cloud of plasma that is pretending to be a rock. Visual, a scale showing 10 billion suns on one side, but the weight of only 40 suns on the other. The scale tips wildly, unable to find balance. How does a star become this empty? The answer lies in the violent, late-stage evolution of the most massive objects in the universe. Stephenson 2-18 didn't start its life this way. Billions of years ago, when it first ignited in the heart of a dense molecular cloud, it was likely a blue supergiant, compact, incredibly hot, and weighing perhaps 50 to 60 times more than our sun. It was a bully in its stellar nursery, accreting gas at a rate that far surpassed its neighbors. But massive stars live fast and die young. While our sun will burn steadily for 10 billion years, a monster like Stephenson 2-18 burns through its fuel in a mere fraction of that time. Once it exhausted the hydrogen in its core, the balance of power shifted. gravity began to lose the war. As the core contracted and heated up to fuse heavier elements, helium, then carbon, neon, and oxygen, the outward radiation pressure became a physical sledgehammer. This pressure pushed the outer layers of the star further and further away from the center. The star began to balloon, moving from a compact blue sphere to the bloated ruby-red titan we see today. But as it expanded, it didn't gain weight. In fact, it did the opposite. It began to starve itself. Visual, a time-lapse of the star's life. It starts as a small, intense blue dot, then slowly swells into a massive, translucent red cloud, shedding glowing veils of gas as it grows. This leads us to the phenomenon of extreme mass loss. Because Stephenson 2-18 is so physically large, the gravity at its outermost edge is a joke. It is thousands of times weaker than the gravity we feel on Earth. At the same time, the star's core is screaming with the light of 440,000 suns. That much light doesn't just shine, it pushes. This creates ferocious stellar winds, charged particles and gas being blasted away from the surface at thousands of kilometers per second. Stephenson 2-18 is literally breathing itself out into the void. It is shedding its own mass at a rate millions of times higher than our sun's solar wind. Over its short life, it may have already exhaled dozens of suns' worth of material. This material doesn't just disappear. It forms a thick, dusty shroud around the star, rich in heavy elements like oxygen, carbon, and silicon. This is why the star appears so cool and red. We aren't just looking at the star. We are looking at the star through its own exhaled breath. This mass loss creates the Eddington crisis we discussed earlier. The star is operating right at the absolute limit of stability. In astrophysics, the Eddington limit is the point where the outward push of light is so strong it completely cancels out the inward pull of gravity. If a star crosses this line, it should theoretically blow itself to smithereens. Stephenson 2-18 is dancing on that razor's edge. Its current mass is so low compared to its luminosity that the star is essentially a stellar nebula that is still trying to hold its core together. Visual. A cross-section of the star. We see the tiny, ultra-dense core fusing heavy elements, surrounded by a massive, hollow-looking envelope of thin, red gas. The outer layers are being stripped away by glowing arrows of radiation. This paradox makes the star incredibly difficult for scientists to model. Most stellar simulations assume a certain level of density and structural integrity, but in Stephenson 2-18, the photosphere, the surface we use to measure its 2,150 radius size, is not a solid thing. It is a luminous web of gas that is so thin it's almost transparent. This is where the lore vault theories get truly wild. If the star is this diffuse and this light, is it possible that we aren't even looking at a single star anymore? Some fringe theories suggest that the mass paradox is actually evidence of a direct collapse in progress. Usually a star dies in a supernova explosion, but some theorists believe that the most massive stars might grow so large and so thin that their cores eventually just give up. Instead of a bang, the core collapses directly into a black hole, and the outer layers, this 10 billion sun volume of gas, are simply left behind to dissipate like smoke in the wind. But there's another possibility, one that ties back to the monster star theory. If Stephenson 2-18 is actually a binary system hidden inside a single bloated envelope, it would explain the mass discrepancy. We might be looking at two stars that have merged, creating a common envelope phase. This would create an object that looks impossibly large but has the mass of two smaller supergiants. It would be a cosmic Frankenstein, a star made of the parts of others, masquerading as a single record-breaking king. Visual. Two stellar cores spiraling around each other inside the massive, lumpy red cloud of Stephenson 2-18. They are churning the gas, contributing to the lumpy appearance of the surface. This lightness of the star has profound implications for its final fate. Because it has shed so much of its outer skin, the star is reaching a stage of advanced chemical maturity. When we use spectroscopy to analyze its light, we see the fingerprints of complex molecules like titanium oxide and vanadium oxide. These are the smoke signals of a dying giant. They can only form in the cool, low-density regions of a star that is reaching the end of its luminous journey. The King of Stars is effectively a cosmic factory, forging the heavy elements that will one day become the building blocks of new planets and perhaps new life. Iron, silicon, and oxygen are being churned in its depths and blasted into the Scutum Centaurus arm by those ferocious stellar winds. But there is a price for this generosity. By shedding its mass so aggressively, Stephenson 2-18 is losing its anchor. The less mass it has, the less gravity it has to hold back the radiation from the core. It is a star in a death spiral, growing larger and thinner every second, moving closer and closer to the day when the balance finally snaps. Visual. The camera pulls back from the star, showing the massive glowing shells of gas it has already shed. The star itself looks like a flickering candle inside a vast red lantern of its own making. This brings us to a haunting realization. When we look at Stephenson 2-18, we aren't seeing a stable, permanent monument of the galaxy. We are seeing a fleeting moment of cosmic chaos. This phase of a star's life, the red supergiant phase, is a blink of an eye in the grand scheme of the universe. It lasts only a few 100,000 years. We just happen to be looking at the right time to see the king at his most bloated and most vulnerable. Is it the largest star because it's the best at being a star? No. It's the largest star because it is the most unstable. Its size is a symptom of its impending death. It is a star that has literally puffed up as its internal systems fail, a giant bubble of fire waiting for the universe to pop it. And yet, even as a hollowed-out ghost, its dominance is absolute. It might have the density of a cloud, but it still has the power to destroy everything in its path. It is a reminder that in the cosmos, scale and mass are two very different things. You don't need to be heavy to be a monster. You just need to be big enough to break the rules. Visual. The star's heartbeat pulse becomes more irregular. We see a massive eruption of plasma from the side, a stellar volcano that dwarfs the entire Earth. But as we look at this impossible object, we have to ask, why is it here? Why did this specific star grow to this specific size in this specific part of the galaxy? To find the answer, we have to stop looking at the star in isolation and start looking at its neighborhood. Because Stephenson 2-18 isn't just an outlier, it's an outcast. It sits on the edge of the most massive cluster of supergiants ever found, and its position there might hold the key to the final mystery of its birth. Was it born a king, or did it steal its crown from the stars around it? Visual. The camera pans away from the hollow star and zooms out to show the Stephenson 2 cluster. Hundreds of red giants glow in the distance, but Stephenson 2-18 sits alone, far from the center, like a sentinel guarding a graveyard. In the next chapter, we dive into the cluster mystery. We're going to find out why the King of Stars is living in exile, and what its lonely position reveals about the violent competition for mass in the deep trenches of the Milky Way. The luminous vacuum of the star's surface, accelerating until the giant red sphere is just one of many lights in a crowded, glittering field. We see a cluster of red stars, all glowing with an eerie, ruby-like intensity. These aren't normal stars. They are all giants. This is the city of giants. To understand why Stephenson 2-18 is so large, we have to stop looking at the star in isolation. We have to look at its neighborhood. In the vast, lonely stretches of the Milky Way, stars usually form in small groups or as isolated wanderers. But there are places, densely packed stellar city-states, where the rules of survival are different. This is the story of the Stephenson 2 cluster, or RSGC2, a massive open cluster that serves as the most crowded nursery of monsters in our galaxy. But here is the mystery. If Stephenson 2-18 is the king, why is it living in exile? The cluster itself was a relatively late discovery in the history of astronomy. It wasn't until 1990 that the astronomer Charles Bruce Stephenson, performing a deep infrared survey, identified this massive assembly of stars. Because it was buried deep within the dust-choked Scutum Centaurus arm, nearly 20,000 light-years away, it had remained invisible to humanity for eons. When the infrared fog was finally lifted, astronomers were stunned. They didn't just find a few stars, they found a cluster containing more than 24 red supergiants. Visual, a 3D map of the cluster. We see about 26 massive red dots clustered in a tight sphere. Then we see one dot, Stephenson 2-18, sitting significantly further out, isolated from the rest of the pack. In the world of astrophysics, the center of a cluster is where the action is. That's where the gas is thickest, where gravity is strongest, and where the most massive stars are typically born. Yet, Stephenson 2-18, the largest and brightest of them all, sits on the outskirts. It is a radical outlier. Mainstream videos will tell you it's a member of the cluster, and they leave it at that. But the lore provided by the University of Tokyo research and the two MASS surveys reveals a fierce debate. Is Stephenson 2-18 actually a member of this cluster, or is it an imposter? Initially, astronomers didn't even want to include it in the cluster's census. Its luminosity was so abnormally high, shining with the light of 440,000 suns, that it seemed to belong to a completely different category of reality than its neighbors. It was like finding a skyscraper in the middle of a suburb. Furthermore, its position at the edge suggested it might be a foreground object, a star that just happened to be in our line of sight, tricking us into thinking it was part of the group. However, follow-up studies and higher resolution spectra eventually tied it to the cluster's outlying group. It is a member, but it is an outcast, and that position tells us something violent about its birth. Visual, a cinematic recreation of the stellar nursery millions of years ago. A massive dark molecular cloud of hydrogen and helium is collapsing. We see thousands of small protostars igniting like fireflies. In the center, several larger stars are forming, but at the edge, one massive vortex of gas is spinning faster than the rest. This brings us to the competitive accretion theory. In a crowded nursery like Stephenson 2, star formation isn't a peaceful process. It's a gravitational war. Massive stars seldom form in isolation. They emerge in dense environments where multiple protostars are all vying for the same limited reservoir of gas. In this cosmic battlefield, some stars become stellar bullies. Because Stephenson 2-18 was likely positioned in a sweet spot at the edge of the initial gas cloud, it was able to draw in material from the surrounding interstellar medium without having to compete with the stars in the dense center. While the stars in the middle of the cluster were fighting over the same scraps of gas, limiting their ultimate size, Stephenson 2-18 was free to gorge itself on a pristine stream of molecular hydrogen. It was a case of competitive accretion on a galactic scale. This star didn't just grow. It stole the mass that could have formed 1,000 suns. It grew so rapidly and became so luminous that it actually began to influence its surroundings. Its intense radiation and ferocious stellar winds started carving cavities in the molecular cloud, blowing away the very gas its neighbors needed to survive. Visual, the stellar bully animation. We see Stephenson 2-18's radiation pressure pushing gas away from smaller nearby protostars, effectively starving them so it can remain the dominant titan. This leads to a fascinating storytelling hook: the king who stole the crown. By consuming so much mass, Stephenson 2-18 became an outlier in the initial mass function, IMF. The IMF is the statistical rule that tells us how many small stars versus large stars a gas cloud should produce. Stephenson 2-18 breaks that rule. It is a 1 in a billion event, a star that managed to circumvent the standard limits of accretion by being in the right place at the right time. But there is a darker side to this isolation. Being an outlier at the edge of the cluster means Stephenson 2-18 is a cosmic engine of feedback. Its luminosity is so extreme, far above the once-believed theoretical limit of 320,000 solar luminosities, that it is actively reshaping the Scutum Centaurus arm. It is ionizing the gas around it, creating vast, glowing H2 regions that serve as both stellar nurseries for the next generation and death zones for any star trying to form too close to the king. Visual. The camera zooms out further, showing the star's radiation clearing a massive bubble in the galactic arm. Inside the bubble, the space is empty and dark, but the edges are glowing with the birth of new, smaller stars, triggered by the pressure of the king's light. However, the cluster mystery doesn't end with its birth. Astronomers are still haunted by the distance paradox we mentioned earlier. If Stephenson 2-18 isn't at the same distance as the cluster, if it's just a foreground ghost, then this entire story of competitive accretion is a myth. But if the outlier position is real, it suggests that Stephenson 2-18 might be part of a monster merger. Some theories in the lore vault suggest that the star's outlying position is the result of a gravitational kick. It's possible that Stephenson 2-18 was born in the dense center of the cluster as a binary system. Through a violent interaction with another massive star, the binary could have been ejected toward the outskirts. During this ejection, the two stars might have merged, creating the bloated, lumpy hypergiant we see today. It wasn't just born a king. It was forged in a collision and then exiled to the edge of the city. Visual. A fast-motion simulation of two massive blue stars colliding in the cluster's core and being slung out toward the camera, slowly turning red and expanding as they travel to their current, outlying home. This is why the star looks so young, yet so evolved. It is a contradiction. Its spectral signatures of titanium oxide and vanadium oxide suggest a star near the end of its life, yet its brightness and position suggest it is still a relative newcomer to the galactic stage. It is a star that has lived 1,000 lives in the span of a few million years. As we look at the king of stars sitting in his lonely throne at the edge of the Scutum Centaurus arm, we realize that its size is not just a measurement, it's a legacy of violence. It is the result of a star that refused to share, a star that bullied its neighbors, and a star that might have even swallowed its own twin to reach this impossible scale. But the universe has a way of punishing such extremes. You cannot be this large, this bright, and this hollow for long. The very gas that Stephenson 2-18 stole from the cluster is now the very thing it is losing at a staggering rate. The king is bleeding. And as we move into the final chapters of its story, we are about to witness the most violent transition in the cosmos. The crown is heavy, and the king is about to fall. Visual. The camera pans across the cluster one last time. The red giants of Stephenson 2 look like rubies, but Stephenson 2-18 glows with a brighter, more unstable light. The music turns somber, with a heavy rhythmic bass line echoing a failing heartbeat. In the next chapter, we look at the Eddington limit. We are going to find out why the star's own light is its greatest enemy, and how it is currently breaching the laws of physics to stay alive for just one more cosmic second. A large holographic screen displays a scale with two weights. One is labeled gravity, and the other light. The scale is trembling violently as the light side begins to press down with overwhelming force. Outside the window, the silent vacuum of space is suddenly illuminated by a deep, throbbing crimson pulse coming from the direction of the Scutum Centaurus arm. In the cold, mathematical heart of astrophysics, there is a point of total structural failure known as the Eddington limit. It is the cosmic red line on the speedometer of the universe. For a star to exist in a state of hydrostatic equilibrium, it must maintain a perfect, delicate balance. Gravity must pull inward with exactly the same force that radiation pressure pushes outward. If gravity wins, the star collapses into a dense remnant. But if light wins, the star begins to tear itself apart from the inside out. For decades, we believed we knew where this limit sat. For a massive red supergiant, theoretical models suggested a maximum luminosity of approximately 320,000 solar luminosities. Anything brighter was considered a physical impossibility, a star that would blow its own skin into the interstellar medium the moment it ignited. Then we found Stephenson 2-18. Visual. A digital readout flashes on the screen. 440,000 L sun. The numbers turn bright red and start to glitch. Stephenson 2-18 doesn't just sit near the limit. It has smashed through it. It shines with the light of 440,000 suns, a luminosity that defies the very laws of stability that govern every other star in the Milky Way. This is the central crisis of the King of Stars. By all our current understanding of physics, this star should not be able to hold itself together. Imagine standing on a ship just outside the star's atmosphere. You wouldn't just see the light, you would feel the physical push of it. At this level of luminosity, photons, particles of light, act like a continuous high-velocity sandstorm. They collide with the gas in the star's outer layers, transferring so much momentum that the gas is literally shoved away from the core. This isn't a gentle breeze, it is a ferocious stellar wind that carries away several solar masses of material every few thousand years. Visual. The camera dives into the star's atmosphere. We see pillars of plasma being blasted into space, moving at thousands of kilometers per second. It looks like a slow-motion explosion that never ends. This extreme luminosity reveals the star's true nature as a mass loss factory. Mainstream videos often treat the star's size as its primary feature, but its mass loss is the real story. Because Stephenson 2-18 has breached the Eddington limit, it is currently undergoing episodic mass ejections. It is effectively shedding its own skin to keep from exploding. When we analyze the spectral fingerprints of this giant using high-resolution spectroscopy, we see the telltale signs of this struggle. We find absorption bands of titanium oxide and vanadium oxide, molecules that can only survive in the cooler, lower-density regions of an atmosphere that has been pushed incredibly far from its heat source. These spectral lines are broad and jagged, indicating vigorous atmospheric turbulence. The star is screaming in the language of light, its outer layers vibrating with shock waves that travel from the deep interior to the edge of the vacuum. Visual. A cross-section of the star. We see the core, intense and white-hot, sending out waves of energy that look like ripples in a pond. As the ripples hit the outer, lumpy surface, they turn into violent shocks that blow gas away in jagged plumes. But there is a mystery hidden in the lore vault that the textbooks are only now starting to address. How does it cheat the limit? If the Eddington limit is absolute, why hasn't Stephenson 2-18 already dissipated into a planetary nebula? The answer may lie in its internal energy transport. In a normal star like the Sun, energy moves outward primarily through radiation and small-scale convection. But in this monster, the convection cells are the size of our entire solar system. These giant, lumpy structures move heat so efficiently that the star might be able to temporarily bypass the standard limits of radiation pressure. However, there is a darker, more controversial theory: the monster merger. In the densely packed City of Giants that is the Stephenson 2 cluster, collisions are not just possible, they are expected. Some astronomers believe that Stephenson 2-18's impossible luminosity of 440,000 suns is the result of a recent merger between two massive stars. This would explain why the star is so bright, but sits on the outskirts of its cluster. The violence of the merger could have kicked the new, bloated king away from the center of the cluster. If this is true, Stephenson 2-18 isn't just a star. It is a cosmic Frankenstein, a hybrid object that is still trying to figure out how to be a single entity. Visual. Two massive red stars slowly spiraling toward each other, their outer envelopes already touching and mixing in a chaotic, fiery dance. As they merge, a single blinding flash of light creates the bloated hypergiant we see today. This breach of the Eddington limit is what makes Stephenson 2-18 a natural laboratory for extreme physics. It allows us to test radiation hydrodynamics under conditions that we could never recreate on Earth. Every photon that reaches our telescopes from this star is a data point in a crisis. It tells us that our models of stellar evolution are incomplete. It suggests that the maximum size of a star is not a fixed number, but a moving target influenced by mass loss, internal mixing, and environmental violence. As we watch this giant breathe out its mass, we are witnessing the twilight of a king. By breaching the limit, Stephenson 2-18 has signed its own death warrant. It is burning through its fuel at a rate that is unsustainable, a fleeting and monumental phase of stellar evolution that few stars ever reach. It is the ultimate expression of the universe's capacity for scale, and its absolute refusal to play by the rules. Visual. The holographic scale in the observatory finally breaks. The light side crashes through the floor as the crimson pulse of the star fills the entire room. The sound of the star's heartbeat becomes a deep, vibrating rumble that shakes the camera. But as the star thins its envelope and its core grows hotter, it is preparing for something even more dramatic than a breach of physics. It is moving toward a final cataclysmic act that will either light up the entire galaxy or vanish into the dark without a sound. Visual. The camera pans away from the star, back toward the distant tiny sun. The light of Stephenson 2-18 casts long, red shadows across the solar system. In the next chapter, we will face the inevitable end. We will explore the quiet giant waiting to explode. Will Stephenson 2-18 go out with the greatest bang in cosmic history, or will it simply disappear? As we pass through the outer lumpy layers of plasma, the light turns from a soft ruby red to a blinding high-energy white. We are descending into the core, where the true violence is hidden. The sound of the star's heartbeat has slowed down, becoming a deep, rhythmic thud that vibrates the very screen. In the vast, silent ocean of the Scutum Centaurus arm, Stephenson 2-18 appears almost peaceful. It is a quiet giant, a ruby-red beacon that has dominated its neighborhood for hundreds of thousands of years. But this peace is a lie. Inside this star, the fundamental forces of the universe are locked in a death struggle, and the king is losing. Every second that passes, this monster moves closer to its own catastrophic collapse, a moment that will either be the most luminous event in the history of the Milky Way or a silent vanishing that defies explanation. To understand why this star is a ticking time bomb, we have to look past its luminous web of an atmosphere and dive straight into its core. The Iron Dead End. For millions of years, this star was a master of transformation. It spent its youth as a massive blue giant, fusing hydrogen into helium with an efficiency that would make our sun look like a flickering candle. But as it aged and swelled into the red supergiant we see today, its internal furnace began to run out of options. It moved through helium, carbon, neon, and oxygen, each stage burning faster and hotter than the last. Right now, in the deepest trenches of Stephenson 2-18, the star is likely approaching the ultimate dead end. Iron. Visual, a 3D animation of the star's core. We see layers like an onion. The outer layers are hydrogen and helium. Moving inward, we see neon, oxygen, and silicon. In the very center, a dark, heavy ball of iron is slowly growing. Iron is the poison of the stellar world. Unlike hydrogen or helium, fusing iron doesn't release energy. It consumes it. The moment the core of Stephenson 2-18 begins to fuse iron, the outward radiation pressure that has held this 10 billion sun volume together for eons will simply vanish. In that heartbeat, the war between gravity and light will end. Gravity, which has been waiting for millions of years to crush this giant, will finally have its way. The supernova versus direct collapse mystery. Most YouTube videos stop here and tell you that a star this big will inevitably go supernova. They promise a flash of light so bright it could be seen during the day on Earth, a spectacular finale that seeds the galaxy with heavy elements. And while a Type 2 supernova or even a massive hypernova is a strong possibility, the lore vault reveals a much more unsettling alternative that standard documentaries completely ignore: the direct collapse. Because Stephenson 2-18 is so incredibly massive, with an initial weight likely over 50 times that of the Sun, It may have too much mass for a supernova explosion to even launch. Visual, a split-screen simulation. On the left, we see a standard supernova. The star collapses and then rebounds in a titanic explosion. On the right, we see the direct collapse. The star simply starts to sink into itself, getting darker and smaller until it suddenly blinks out of existence, replaced by a black hole. This is the quiet giant theory. In a direct collapse, the core becomes so dense so quickly that it forms a black hole before the shockwave can reach the surface. Instead of the greatest fireworks show in history, the largest star ever discovered would simply disappear. No flash, no bang, no memory. One moment, the king is there. The next, there is only a gravitational sinkhole 19,000 light-years away. The aftermath, a legacy of matter. Whether it ends in a violent explosion or a silent collapse, the death of Stephenson 2-18 is a requirement for the future of the galaxy. As we've seen, this star is a cosmic factory. Through its ferocious stellar winds and its eventual death throes, it is currently shedding layers rich in carbon, oxygen, and nitrogen. Visual. The camera pulls back to show the Stephenson 2 cluster. We see the shells of gas the star has already shed, glowing like a nebula. These clouds are the raw materials for the next generation. These aren't just waste products of a dying star. These are the building blocks of everything. The iron in your blood, the oxygen in your lungs, and the silicon in your smartphone were all forged in the belly of a giant like this. Stephenson 2-18 is breathing out the future of the Milky Way. It is a vital contributor to the galactic chemical enrichment. If it goes supernova, it will scatter these elements across thousands of light years, triggering the birth of new stars and perhaps new worlds. If it collapses directly, it will still leave behind a massive supernova remnant, a glowing shell of gas that will shine for tens of thousands of years as a tombstone for the king. The ticking clock. How much time does the king have left? In cosmic terms, Stephenson 2-18 is already dead. It is in a fleeting monumental phase that few stars ever reach and none can sustain. Because it is burning fuel at such an extreme rate, its life is measured in thousands of years, not billions. Visual. A digital countdown timer appearing over the star. The numbers are blurring as they tick down. The star's lumpy surface is pulsating irregularly, like a heart undergoing an arrhythmia. This instability is visible in its light curve. Astronomers have observed that the star's brightness isn't constant. It fluctuates and pulses, a sign that the internal structure is becoming increasingly chaotic. These are the final breaths of a giant. Each pulse is a shockwave propagating from the core to the surface, a warning that the cosmic limit we discussed in Chapter 3 is no longer just a theory, it's an active threat. The ultimate perspective. In the end, Stephenson 2-18 serves as a natural laboratory for the extremes of our universe. It pushes our technology, our math, and our very intuition to the breaking point. It reminds us that size in the universe is temporary, and that even the most dominant giants are subject to the same laws of decay as a single grain of sand. As we watch this quiet giant wait for its end, we realize that we are witnessing one of the most rare and transient moments in the history of the Scutum Centaurus arm. We are looking at a star that has reached the absolute pinnacle of stellar achievement, only to find that at the top of the mountain there is nowhere left to go but down, straight into the heart of a black hole. Visual. The screen begins to darken as the star's red glow fades into deep purple. The camera pulls back one last time, leaving Stephenson 2-18 as a single flickering dot in the massive star-rich spiral arm. The king is waiting. The iron is forming. And the universe is prepared to continue on, with or without a witness to the final fall of the largest star ever discovered. As the camera retreats, we see the person is an astronomer, then the observatory, then the Earth, then the solar system. The sun shrinks until it is just a memory. We continue moving until we are staring back at the entire Milky Way galaxy, a swirling mosaic of 100 billion stars. A single, bright red point of light, Stephenson 2-18, pulses in the Scutum Centaurus arm. We have traveled 19,000 light-years into the dark forest between the stars, searching for the largest object the Milky Way has ever dared to create. We have stood on the threshold of a star that holds the volume of 10 billion suns, a behemoth that swallows the orbits of every planet we have ever known, from Mercury to the Lord of the Rings, Saturn. But as we reach the end of this journey, we find that the story of Stephenson 2-18 is not really about the star at all. It is a story about us. It is a philosophical mirror, a cosmic benchmark that reflects the absolute limits of human observation, human mathematics, and the human spirit. For centuries, we believed our sun was the ultimate reference point. It was the source of all warmth, all life. It was the stable, perfect anchor that defined our reality. But when we place the sun next to this monster, the comparison stops working. Our intuition, built on the pale blue dot we call home, simply cannot follow. Stephenson 2-18 represents a different category of reality. It forces us to confront a terrifying truth. The universe does not operate on a human scale. The crisis of the impossible. Throughout this documentary, we have returned to the same number, 1,500 solar radii. For decades, this was our cosmic limit, the theoretical wall where physics supposedly broke down. We believed that no star could grow larger than this without being torn apart by its own light, and yet Stephenson 2-18 exists at 2,150 solar radii. This creates the first and most profound reflection in our philosophical mirror. Why were we so sure of the 1,500 limit? It was because our models were based on what we could see and what we could calculate from the comfort of our own solar neighborhood. Stephenson 2-18 is the star that shouldn't exist. Its very existence is a reminder that our scientific laws are often just temporary maps of an infinite territory. When the star breaks the rule, it isn't the star that is wrong. It's our understanding. It prompts a re-evaluation of stellar models and reminds us that we are still children playing with blocks in the shadow of a cathedral we don't yet understand. The illusion of certainty. As we peer through the infrared fog that once hid this king from our sight, we encounter the measurement illusion. We have discussed the distance paradox, the fact that if our calculation of 19,000 light-years is off by even a fraction, the king of stars might just be a regular giant wearing a mask of dust. This reflects a deeper philosophical uncertainty. We live in an age where we can resolve the disk of a star thousands of light-years away using interferometry, yet we are still guessing in the dark about the fundamental properties of the largest object in our galaxy. The star is lumpy, its surface a luminous web of plasma that defies a clear boundary. It is a star that is breathing, losing mass at a staggering rate, and potentially cheating its way to size through a monster merger. When we look at Stephenson 2-18, we are looking at the edge of cosmic scale. We are forced to admit that our precision tools, our infrared telescopes like Spitzer and Gaia, are still battling against the distortions of the interstellar medium. The star is a reminder of the relentless pursuit of understanding. We keep building bigger telescopes, not just to see more, but to find out how much we were wrong about yesterday, the king who stole the future. In Chapter 7, we explored the cluster mystery, the fact that this king sits in exile at the edge of the Stephenson 2 cluster. This isolation provides a haunting metaphor for cosmic dominance. If the competitive accretion theory is true, this star grew to its impossible size by bullying its neighbors, stealing the gas that could have formed 1,000 suns. There is a cold Darwinian logic to the heavens. In the Stephenson 2 cluster, size shows no mercy. The star's dominance is absolute, but it is also its death warrant. By becoming so large, it has become transient. It is burning its fuel at an extreme rate, racing toward a final collapse. This is the mass-radius paradox in a philosophical light. To be the greatest, the star had to become the emptiest. It is a hollowed-out ghost, a luminous vacuum that has traded its stability for a brief, monumental moment of fame in the cosmic record. It is a monument to nature's capacity for generating objects of unimaginable scale, but it is a monument built on a foundation of instability. The gift of the dead king. But even as the king bleeds his mass into the void, he is performing the most important act in the universe: galactic enrichment. The heavy elements, the carbon, oxygen, and nitrogen flowing through your veins right now, were forged in the belly of a giant exactly like this. Stephenson 2-18 is a cosmic factory. As it sheds its outer layers through intense stellar winds, it is seeding the galaxy. The death of this star is not an end. It is a continual cycle of renewal. Whether it ends in a spectacular supernova or a silent, direct collapse into a black hole, its legacy is inscribed in the atoms of future worlds. There is a profound interconnectedness here. The microscopic particles in Stephenson 2-18's atmosphere are connected to the grander questions of our own origin. We are not separate from the monster star. We are its children. The star dies so that the universe can continue to evolve. It is a shining example of how technological innovation, collaborative effort, and relentless curiosity can connect us to a narrative of creation, transformation, and destruction on an unfathomable scale. The meaning we choose. In the end, Stephenson 2-18 is just a ball of hydrogen and helium, a plasma soup governed by gravity and light. It does not know it is the largest. It does not know it is a king. As the transcripts tell us, the universe will continue on without witnesses, without memory, without meaning. The only meaning that exists is the one we choose to give it. We choose to view this star as a challenge to our perception. We choose to see its impossible size as an invitation to wonder. We choose to spend our brief lives building telescopes to catch a single photon arriving from 19,000 light-years away, because we believe that the secrets hidden in that light can tell us who we are. Stephenson 2-18 is a mirror because it reveals our own humility and our own grandeur. It dwarfs us in scale, but it cannot match us in curiosity. We are the tiny sparks in a vast cosmic story, yet we are the only ones capable of writing that story down. Final reflection. Visual. The camera zooms back into the astronomer's eye. We see the reflection of the red star one last time before it fades. The screen transitions to a final, stunning view of the pale blue dot Earth hanging in the immense, star-studded void. When you look up tonight, remember that the night sky will never feel the same again. Behind the familiar stars of the Big Dipper and Orion, hidden in the infrared fog of the Scutum Centaurus arm, sits a king. He is bloated, lumpy, and impossible. He is a quiet giant, waiting for the iron to form in his core. He is a reminder that the universe is dynamic, diverse, and unpredictable. But most of all, he is a reminder that as long as we keep looking up, as long as we keep deciphering the signals, we are part of something much larger than a single star. The crown is heavy, the king is temporary, but the meaning we find in his light, that is eternal. Visual. Fade to black. The sound of the star's heartbeat thumps once, then silence.